So this lecture is about two-port networks. Uh, a port is a collection of two terminals in an uh, electric network. So if you have a network and you take two terminals out of it, suppose this is your network, and you somehow connect one terminal to one node inside, another terminal to another node inside, what you get is a port, right? So uh, port is completely specified when the voltage current relationship is of the terminals is given, right? So the one port network would be completely specified if the current voltage relationship at the terminals, if V comma I relationship at the terminals is given, is specified, right? So you have something like this: a voltage, a terminal voltage, port voltage, and a port current. And it's also important to understand that a port may be regarded as a pair of terminals, as a pair of terminals, where terminals basically mean connection to a node inside the circuit. So a port is a pair of terminals in which current into one terminal, in which current into one terminal, into one terminal equals the current out of the other, equals the current out of the other. So without explicitly drawing it here, actually the current out of this terminal is equal to I, right? So this is a one port network, and it is completely specified if you specify V and you specify I, the terminal voltage and the port voltage and the port current. Now, two-port networks are ones, as the name suggests, in which you will actually be taking out four terminals, right? So one would be the input side, right? You would call this maybe V1, I1, and this terminal 1 and this terminal 1 dash, and the other would be the output side. So this will be your terminal 2, this will be your terminal 2 dash, and the current is normally drawn inwards, right? So this is your standard two-port network. So you have taken out four terminals and labeled your currents and voltages as follows. It is understood that this current, outgoing current here, is equal to I1, and this outgoing current here out of the terminal 2 dash is equal to I2, but it is not generally shown explicitly. Now, again, so since you have four variables now at the ports, so you have V1 and I1 at input port, V2 and I2 at the output port. So you will be able to completely specify your two-port network if you know the relationship between these four parameters. Just like the relationship between two parameters specifies the one-port network, the relationship between the four parameters specifies the two-port network. Now, why do we have two-port networks, and why do we model certain networks as two-port networks? Is because they are very prevalent throughout uh, network theory circuit analysis. Like, for example, your transmission line is a two-port network. Transmission line has a sending end where you're sending power and a receiving end where you're receiving power. So you have a sending end voltage, a sending end current, right? And you have a network in between consisting of transmission lines, transformers, right? And then you have a receiving end where you have a receiving end voltage and receiving end current, right? So so a transmission line is a typical example of a two-port network. Similarly, many devices can be modeled as two-port networks. For example, transistors can be modeled. Transistors, the analog transistor can be modeled as a two-port network. So it is very important to study two-port network as far as circuit theory is concerned. Now, coming back to the fact that we have four variables, V1, I1, V2, I2, we can have different types of representations of two-port networks depending upon which parameter is dependent and which parameter is independent. So typically, two parameters out of the four are taken as dependent. Two parameters are dependent and two parameters are taken as independent. Two parameters are taken as independent. So for example, the first parameter that we talk about, the Z parameters. In this, you take your voltage as a dependent parameter. So voltage would be a linear combination of the current. Here your voltage is again going to be, the second voltage is also going to be a linear combination of the two currents. Normally you'll have all these voltages, currents and impedances. These are impedances because you can see that Z11 is actually a ratio of V1 by I1 if you have this current as 0. Normally these are all functions of S and the complex frequency variable because in general you can represent any voltage or current that you normally find in circuits as a function of S, So these impedances would also be functions of S. So you could also write this as V1S is equal to like this, which would be perhaps a more mathematically correct representation. But in any case, it is understood that these are general representations and these quantities would be in general functions of S. These are not always going to be DC quantities, right? So you can see that these are called the Z parameters because they will all have units of ohms, units of impedance, right? So Z11 is V1 by I1. Similarly, Z12 can be written as V1 by I2 for I1 equal to 0, and you can write down the same for Z21 and Z22. So these are open circuit parameters because the parameters are specified when the current at the other port is 0, right? And we can see that this is a driving point parameter because both the voltage and the current are specified at the same port, which is port 1. So we can say that Z11 is a driving point open circuit, and since it is at the input side, you can say it's a driving point open circuit input impedance, right? Similarly, Z22 will be driving point open circuit output impedance. As you can see that Z22 is V2 by I2 for I1 equal to 0, and Z12 and Z21, these are both transfer transfer parameters, because the two the two the ratio of Z12 is the ratio of two parameters which are measured at two different ports, right? So these will be called transfer open circuit impedances, right? And if uh, the open circuit transfer impedances of these two ports are equal, if Z12 is equal to Z21, we say that this network is reciprocal, right? So it's very easy to find these parameters for uh, general circuit by using nodal analysis. We can write the general nodal equations and find out the parameters for Z parameters for any circuit. In general, for a T circuit, it is very simple to find the two parameters, and we can write the Z parameters by inspection for the T circuit. So if you have the input port V1 I1, the output port V2 I2, and you have these impedances ZA, ZC, and ZB, you can see that if you're looking at the input impedance from this side when you're open circuiting the other port, so you can straight away write by inspection that Z11 is going to be ZA plus ZB. So this is a standard T circuit. It's in the shape of a T. In a similar way, you can write down Z22. From here, if you look at the impedance that will be faced by a source applied on this side, it is going to be ZC plus ZB. And if you look at the transfer parameters, where you're looking, for example, at Z12, which is V1, as we have seen, which is V1 by I2, for I1 equal to 0. So we have to open circuit this side, and then we have to see the relationship between this voltage and this current here. So when this side is open circuited, this means that this I2 current is going to flow completely through this. So I2 into ZB is going to be equal to V1. So I2 ZB is going to be V1. That means V1 by I2 is equal to ZB. So this Z12 will be equal to Z21. This is a reciprocal network, and this is going to be equal to ZB. So just like we define Z parameters, in a similar way, we can define the Y parameters. The only difference would now be that in the Y parameters, the currents are going to be independent. Currents are going to be defined as independent. So you have Y11 V1 plus Y12 V2, Y21 V1 plus Y22 V2. And again, we can independently uh, find out these parameters. You can say Y11 is equal to I1 by V1 for V2 equal to 0. So we can see that these parameters are admittance parameters, and they are short circuit parameters. So for example, Y1 is driving point. Y11 is driving point because both these measurements are taken at the input port. At one port, driving point short circuit because V2 is equal to 0, input admittance, right? And similarly, Y22 would be driving point short circuit output admittance, and Y12 and Y21 would be short circuit transfer admittances, right? So again, we can find out using this relationship, we can find out the Y parameters for any circuit. Normally, if the circuit is complex, we will be applying mesh analysis to find out the equations. But in general, if you have a simple circuit, for example, the standard pi circuit, you can write down the Y parameters by inspection. So for example, you have, this is your input port, this is your output port, and you have these admittances here, YC, YA, YB. If you're looking from this side and you're looking at the admittance when you short circuit on the output, that is, you're looking at Y11, you can see very clearly that it will be, when you short circuit here, it will be YA and YC in parallel. So when two admittances are in parallel, you just add them up, right? Impedances in parallel, you have a formula for that, but admittances you can add up. So it is very easy to see from inspection that Y11 is YA plus YC, Y22 is YB plus YC, and Y12, now for example, Y12 is going to be V1. If you look at the formula here, Y12 is going to be I1 by V2. I1 by V2 for V1 equal to 0. So you need to have a short circuit here because your V1 is 0. And then you need to see the relationship between the current that is flowing here and the voltage that is applied here. So if you apply a voltage here and you short circuit this side, what is the current that is going to flow uh, in the short circuit, right? If you look at the short circuit, the equivalent circuit would be something like this. Now it's going to be YC, YB, and you have applied a voltage V2, and you are saying that this current, that the current that is flowing in the short circuit, because uh, this side is this current in this direction, this current in this direction is your I1, isn't it? Because your I1 is like this. So if you take these two terminals out, this is the current that is actually flowing in from this side. So if you look at this relationship, you can see that the current in this branch here from this direction is just V2 into YC, and this is equal to minus I1. Yeah, so you can write down that I1 by V2 is equal to minus YC, right? And so automatically your parameter Y12 is equal to Y21 is going to come out to be minus YC. So this is how you find out your parameters. I will try to make this more clear. Uh, if you have a short circuit on this side, you basically your overall two-port network is going to be something like this. Right? This is your two-port network, and what you have done, uh, you have short circuited this port. Let me just explain it slightly more because I think it needs a little more explanation. So I have short circuited this port, and this is my YA, and I'm now looking at this current. So because there's a this current is my input port current I1, right? And this is my if I look at this the result of this short circuit is that this admittance here can be neglected. So I can remove this. Now when I look at this network, the current in this branch here is just this impedance multiplied with this admittance. So the current in this direction is V2YC, and from the connections that we have, the labeling that we have, this current in blue is the opposite of the current here. So V2YC is equal to minus I1, and from here we can easily see that Y21 is minus YC. So in this case, in the pi circuit, the Y21 is equal to Y12, and this is equal to minus YC, right? So this was about the Y parameters, which are short circuit admittance parameters. There's one more thing that we need to know, and that is if Y11 is equal to Y22, we say that the network is symmetrical, right? In a similar way, we can define two other parameters, the H parameters, in which basically we have V1 and I2 as dependent parameters, and we have these, we call them hybrid because they have hybrid units. Some are units of impedance, some parameters, and some parameters have impedance units of admittance. So this is I1, V2. So H11, H12, H21, H22, I1, V2. These are called the H parameters, and we can open them up and you can see very clearly that H11 is V1 by I1, V2 equal to 0, right? So it is a short circuit input impedance, right? Or we can also see that it is just the reciprocal of 1 by Y11 because your Y11 was defined as I1 by V1 for V2 equal to 0, right? Similarly, you can see that H22 is equal to I2 by V2 for I1 equal to 0. So it is an open circuit uh, driving point, open circuit output admittance, and you can see that because it's an open circuit parameter, it is equal to 1 by Z22. And then your H21 and H12, these are transfer parameters, right? Similarly, you have the ABCD parameters. The ABCD parameters are used extensively in modeling power systems, transmission lines. We have the sending end voltage as dependent on the receiving end voltage, and the receiver receives a current minus I2, so you have minus I2 here, and you define the parameters as A, B, C, and D. The reciprocity condition in this, as we have already seen, for reciprocal networks, Z12 is equal to Z21. For reciprocity, AD minus BC is equal to 1. And we can derive it by expressing ABCD parameters in terms of Z parameters, and we'll see that this is the reciprocity condition. Again, some of the parameters are open circuit parameters and some parameters are short circuit parameters. Like for example, A, if you see A is equal to V1 by V2 for I2 equal to 0. So what is A? A is, and so this is an open circuit, right? So it's an open circuit and it's a transfer parameter. So it's an open circuit voltage ratio transfer function, right? And we can see that if we look at this I2 equal to open circuit parameters, we see that A can be given as Z11 divided by Z21, because for both Z11 and Z21 we make I2 equal to 0, and if we take the ratio of these impedances we'll get A. Similarly, the D parameter is minus Y11 by Y21, and the B parameter is a transfer parameter, is equal to minus 1 by Y21, and the C parameter is again a transfer parameter equal to 1 by Z21. So if you just multiply AD and BC, you should be able to get, for this reciprocity condition, AD minus BC should be equal to 1. So these are the basic parameters. We can express some standard, for example, electrical engineering systems, like for example a transformer. If you want to, we can express in terms of the ABCD parameters. For example, this is an N:1 transformer. This can be regarded as a two-port network. So this is your input port, this is your output port, this is your current here, input current. Output current, we know for a transformer which is N:1, V1 by V2 is equal to N by 1, and I1 by I2 would be equal to 1 by N. Because of the direction of current that we have here, we'll have to write minus 1 by N. So if you want to express V1 in terms of V2 and I1 in terms of I2, and then write these as ABCD parameters, we see that this is N minus 1 by N. Sorry, if your minus sign is here, then we don't need to write minus here. So these are the ABCD parameters for the N:1 transform. Right? So this was a general introduction about two-port networks. In the next lecture, we are going to see the relationship between two-port networks and how to connect two-port networks in different types of connections. Thank you very much.